Okay, so the first topic is induction. Okay, and induction is basically the process of giving one, how come that's not, okay, process of giving one object a net electric charge without touching the object to a second charge object. All right, and I'll have a demonstration for this later. So if we've got a conductor, remember a conductor's got free charges that can move along, and we somehow move a negative charge next to it without touching it, all the positive charges accumulate on one side and all the negative charges accumulate on the other. All right. Then what we do is we ground the metal sphere. In other words, we connect it to something that takes the negative charges away. Okay, because the positive charges, they're still being held in place there because of that negative charge. Okay, and then if we take the grounding wire away, we leave this so that it's just positively charged. Okay, so you just need to know the steps of induction, how you can make a conductor charged using this particular process. Okay, that's all you need to know there. Equipotential surfaces also come up on the AP test. All right, so equipotential surface is a surface on which the electric potential is the same everywhere. All right, so for example, if this is a positive charge right here, and I took a negative charge right there, if I had a negative charge and I moved it anywhere along this surface, okay, that would take no work. All right, so doing that does no work. All right. It says for a point charge, the equipotential surfaces are concentric spheres, just like what you're looking at there. The equation for potential about a point is that. So since wherever R is the same, the potential is the same. Okay, so no net electric force does no work as a charge moves on an equipotential surface. All right, and just shows you the math for that. So the equivalent for us would be, let's say, Christian Clarion was, since we're throwing him under the bus, let's say Christian Clarion was climbing up some mountain. All right, and he stayed right there. Okay. Does he do any work in the vertical direction if he stays just on that same ledge right there? No. Okay, so that's what it's basically saying. You're staying the same distance away. So this R is the same everywhere. Okay, that R is the same everywhere. So you're doing no work as long as you're moving along that surface. Okay, so you just need to know that there's no work done as long as you're moving on the same equipotential surface. All right, the electric field created by a group of charges is everywhere perpendicular to the associated equipotential surfaces and points in the direction of the decreasing potential. All right, so we already knew that electric fields point in the direction of decreasing potentials. All right, so in other words, we already knew that if you've got a electric field like this, the region of the low V would be here, and this would be the region of the high potential. Okay, we already talked about that. But what we didn't talk about is the fact that if you look everywhere, okay, the electric field line is always perpendicular, okay, always 90 degrees to the equipotential line. All right, so that's the important part right there, that they're perpendicular to equipotential lines. All right? Okay, just some more facts. Conductor equipotentials. Okay, a conductor, its surface is at an equipotential. All right, so what happens when two conductors are connected to a wire? All right, so if I connect those two, which one's got more charge, the one on the left or the one on the right? The one on the left. So what happens to the charges if I connect them with a wire? Yeah, they'll balance out. So these ones will move over there. Okay, so that's all you need to know there. Pretty straightforward stuff. For capacitors, now we're going to get into capacitors a little more, but we're going to just describe what a capacitor is. A capacitor is two conductors of any shape placed near one another without touching. Okay, a capacitor is able to store charge. All right, now dielectrics. This really isn't super important for us, but let's talk about them Anyway, so it says an electrically insulating material filling the region between the plates. Okay, when there is no dielectric materials for a capacitor, the dielectric constant for such an application will equal 1. So kappa, that symbol is kappa equals 1. So for us, kappa will always equal 1. Okay, because we're not going to use dielectric materials. Okay, a parallel plate capacitor. Okay, it says a parallel plate capacitor has a positive plate that contains positive Q charges, while a negative plate contains negative Q charges. Between them, there exists a potential difference of V. Experimentation shows that an increase of Q causes a proportional increase in V. So the ratio of the amount of charge, okay, over the amount of electric potential is what we call capacitance, right? And its unit is the farad. Okay, we'll get into this a little more later, all right? But for right now, all we need to know is that relationship. The capacitance is the amount of charge per unit voltage or per unit potential. Okay, all right. Some other things, the capacitance of a parallel capacitor. This is the equation on your equation sheet that you need to know for a capacitor. Generally speaking, we don't solve this equation on the free response part of the test. What's really more important is knowing the relationship between the capacitance and the area of the capacitor and the distance between the between them. Okay, between the two parallel plates. Okay, so the area of the capacitor, so let's look at, so this, in the previous picture we were drawing the two parallel plates. Okay, this value D is how far apart they are. Oh, that's in the previous picture, right? And the area A is equal to this base and this height. So the area is equal to the base times the height. Okay, so that means when the area increases, according to this equation here, when I increase the area, what does that do to the capacitance? Okay, yeah, it increases the capacitance. That means it can hold more charges per unit potential. All right, but what if we increase the distance between them, between the two plates? What does that do? Okay, that decreases the capacitance. Okay, and we're going to talk about capacitors more. We're just going to touch on it this time. Okay, probably more important for your WebAssign is how we can calculate the energy stored in a capacitor. Okay, it says the total work done by a battery in completely charging a capacitor is a product of the total charge Q and the average potential difference. So basically, what we do here is we prove this equation. Okay. We end up proving that equation there, that the amount of potential energy stored in a capacitor can be calculated by using 1/2 QV, right, or 1/2 CV squared. And that's on your equation sheets. So again, these are a couple equations that they basically just need to be memorized. All right, for
get the equation sheet on the multiple choice.
You don't get the on the multiple choice, and this topic comes up on the multiple choice. That's why it's so important to have these memorized. Okay. All right. Is that equation on your notes? What's that? Yes. Yeah. Okay. All right. So what I want to do now is I just want to go over some of the questions that might be covered on the WebAssign. Okay. Remember, on the WebAssign, there's going to be some questions that discuss the direction of the electric field. Okay, so if this is the direction of the electric field, are the lower potentials on the left or the right? On the right. So let's say that that's like negative 10 volts, this is 0 volts, and this is positive 10 volts. Okay, so this arrow represents the direction of the electric field. So you're going to have to apply this equation. Okay, you're going to have to apply this equation for the electric field, negative V over D. All right, for some of those equations. And you'll also have to be applying, so that's for a particular question on the WebAssign, and also we have to go back to, because the WebAssign's got a lot of review stuff. Remember, the electric field is KQ over R squared, okay, and also the U, which is the electrical potential energy, is equal to QV. All right, but if you got two charges, it would be equal to KQQ over R. Okay, that's for the energy. So I'm bringing up these equations again because they are going to be part of your review. Okay, the WebAssign is a review today. The WebAssign is actually going to be pretty easy. I think the stuff for homework is going to be easy because I want you guys to spend some of the time studying for the big quiz.
So this stuff is not going to be a big quiz?
No. Only the stuff on the stuff that I showed you earlier. Okay, that's going to be part of the big quiz. Okay? All right, and today's quiz covers, what's the topic? The electrical potential energy. No, the electrical... I forgot what that... Well, what was the last quiz on? What was last night's topic on?
I did it. Where is the charge potential equal 0? It was electric potential from a point charge.
Okay, yeah, the electric potential from a point charge. The one where there's location 1 and location 2.
Yeah.
Okay, so on today's quiz, oh look, there's some space there. So today's quiz is going to cover, like, there's like a location 1, right? Then there's a location 2, and there's like a negative, there's either like a positive or a negative charge out here. Okay, and that causes, and there's a certain distance, let's call that R1 and this R2, right? And you're supposed to calculate the potential here, V1. What equation would that be? Okay, KQ over R, that would be R1, and that would be KQ over R2, right? What Q are we using there in that equation? Yeah, it's this Q right there. It's that point charge, right? So that gives you two different V's. That gives you a V there and a V there, right? Then it asks you a question like, what does it take to move like an electron, like from there to there, right? How much work that would take? Is that what it asks you to do? Something along those lines. And how would you do that? What? That would be work, so that would equal U, and you'd have to do what? What's that? Q, but it would be this Q right here, though, right? That Q, right? So let's call that Q negative, that Q negative, and you would go final V, so that'd be V1 minus V2, right? Was that what the thermal physics was about? Yeah. Okay. So I think that was pretty thorough. So please work on.